Awesome. Thank you, Peter. So for those of you who are with Perconi, you know that the marketing department has a lot of fun with personal photos. I tried to find one of Peter at 15. There is no evidence that he was ever 15, as far as I could tell. He somehow just wiped all the databases clean, and he got to his mother before I did. So we'll try to set something up for next year if we can. So our next keynote is polyglot persistence at Facebook. And I'd like to invite Harrison Fisk up. Harrison is a member of the Facebook database performance team. He previously worked at MySQL AB for 8 years as a trainer and support engineer. And he's also co-authored a book, MySQL Clustering. So please give a warm round of applause to Harrison Fisk.
All right, so thank you, Jim. So my name is Harrison Fisk. I'm on the data performance team at Facebook. And today I'm going to talk to you a little bit about how we think about data at Facebook. So the first thing I want to start off with is a quote. So database luminary Michael Stonebraker recently gave an interview where he talked about Facebook's data problems. So one of his big quotes was, I would say they have the hardest database problem on the planet. I appreciate the sentiment. I don't know if it's the hardest, but it definitely is a hard problem that we deal with all the time. The second part of his quote I want to bring up is they would love to get rid of MySQL. So this is a common misconception. And part of that misconception comes from how we think about and deal with data at Facebook. So the title of my talk is Polyglot Persistence. So what is this? Well, this is just basically a fancy term for the idea of using different data storage technologies to handle different data storage needs. So rather than having one data storage system, MySQL or otherwise, that handles everything, we instead use many different ones in order to serve our data, in order to make performance, efficiency, all of these gains that we can do. So thinking more about how we think about data at Facebook. So I said we use lots of different stores. Obviously, having many different storage technologies adds a lot of complex overhead for operational needs, for backups, recoveries, all these sorts of things that you need to think about. So we try to follow an idea of as many as necessary, as few as possible. So we want to basically have ones that are best in class for what they do, and then reuse those. However, again, what they do with the actual niche can actually be different for all these different storage technologies. So I'll actually go over and talk about some of the different options we use and kind of how they fit into our thoughts around data. So next is problem-centric, not technology-centric. So when we're looking at how we want to create some new application, we don't go in and say, hey, we're going to use MySQL for this. Instead, we basically will look at all the different needs of the application. I'll go over the different needs and how we analyze and figure this out. But we'll figure out what exactly the problem needs in order to solve the issue. We don't ever go in and say, hey, we should use MySQL for this. We instead figure out what the problem is and then go based on there. So next thing I want to talk about is a little bit about Facebook's engineering culture. So Facebook follows something called the hacker way. So you may have heard the phrase move fast and break things. Essentially what we want to do is we want to make it very easy for our engineers to build, to innovate, to develop new applications, new features, and so on. Now on the data side, we think of this a little bit different. We don't really want to break our data stores. So we follow this setup here. So make it work, make it fast, and make it efficient. So the first part, make it work. Again, we want to make this as easy to use for our developers to consume and build new applications. So this is the idea of just getting it working. They can prototype. They can use it very easy. Developer efficiency falls into this category. It's very, very important for us to ensure that our developers have a good experience and want to use our different solutions. 2, make it fast. So we have a lot of users of Facebook, so we need to be able to handle the full scale, make it fast and efficient for everyone to access. And then finally, make it efficient. So obviously, if we can reduce the number of servers, reduce the overall expenses for different features, it's a very important concept as well when you're dealing with our scale. All right, so I talked about things being problem-centric, not technology-centric. So what are the different aspects we look at when we have some new problem and we want to try to solve? So the first thing we look at is data size. Pretty straightforward. How much data do you need to store? Is it going to be a couple gigs? Is it going to be terabytes? Is it going to be petabytes? Is it going to be hundreds of petabytes? How much data are we talking about here? That's a very straightforward one. Normally pretty easy to come up with some idea. Also, the growth of data storage is very important as well. Is it going to start off small and grow to big, or do we need to preload a bunch of data? Do we need to pre-allocate all the resources? Those sorts of concepts as well. Next, what is your access pattern? So how are you going to be reading data? Are you going to be reading it based on most recent data, maybe not accessing old data quite as much? We have different access patterns of data. For example, at Facebook, the fact you're friends with someone doesn't matter when you became friends with them. So that always matters. We're always going to access it, regardless of whether you became friends 3 days ago or 10 years ago. We still care about that data. We're still going to be accessing that data constantly. We have some other data that's much more temporal in nature. So for example, with timeline, when you're viewing someone's profile, things like that, the most recent posts get hit a lot. Older data, from 3 years ago, much less accessed. So we're able to build based upon the access pattern. So even though the data size may be large, there may be great skew in how you actually read that data. Data velocity. So how fast does data flow through the system? So in some cases, the data may not be that large that we store permanently, but the incoming data may be very, very high. We may have very aggressive purge processes, things like that. So you may actually have many gigs being ingested, and then, but you're deleting multiple gigs as well, so you're actually keeping the overall data size very small. But the actual overall data velocity through the system is an important concept as well. Next, query size. So obviously, I don't mean the actual query text size, but like how much data are you reading? Do you need to process gigs of data, megs, kilobytes, single rows? How much data is actually being processed across here? So obviously, we need to figure out how much data we can read to help determine the amount of queries and the types of queries that you're able to do as well. Query latency. How fast do your queries need to be? Is it OK that they take hours? Do they need to take seconds, split seconds? Obviously, if something's going to be user-facing, on a web page, we need to have, millisecond type latency. But if it's going to be something that runs nightly, hours, things like that could be possibly fine. And the final thing we need to look at is availability. So how available does the solution need to be? So different storage technologies have a lot of different availability trade-offs. And we need to figure out, do you need to be available all the time? Is it OK if there's some downtime sometimes? For example, an internal facing application, it could be OK that it's offline for an hour. It's not going to be the end of the world. If Facebook is down for an hour, as far as we're concerned, it's the end of the world. So based on all these different things, we kind of have a bunch of trade-offs. So we need to look at all the different options, all the different storage solutions, look at hardware, things like that, all get influenced by this. Obviously, in the ideal world, everything takes a split second. We can store hundreds of petabytes of data, real-time access, distributed, blah, 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 all these sorts of things. Practically speaking, because of efficiency reasons, we need to think a lot more about storage mediums, figure out what storage solutions make sense in order to use for the different solutions. So now let's take a look at some of the different options that we actually use for storage at Facebook. I'll give some stats as well to give kind of an idea about the size of our systems. So in this chart here, I've broken it down by 2 axes. We have data size and query time. I did talk about a lot of other things, query velocity, all these other things. But I'm just going to give a breakdown of these 2 axes for actually figuring out our different data systems. So now from here, we can divide this into 4 quadrants. So these 4 quadrants, we have data size, query efficiency, now break down into some of the well-known data paradigms. So for example, if we have large data, we have long queries. What category of applications go into here? Big data. Never thought I'd say that word in a keynote, but I'm talking about big data now. So we have big data. So now if we go to the opposite corner, we go to the bottom left corner there. What's the opposite of big data? Small data, as we call it. So small data doesn't necessarily mean small data, but the idea here is this is more of the transaction processing systems. So these are the real-time querying, the actual execution of very small, discrete operations, returning very small result sets. So now we get into some more interesting things. So if we have very large data sizes, but we need very, very short response times, millisecond type response times across petabytes of data, what sort of solutions do we use for that? Well, it turns out there isn't really a single solution for this. So this is where a lot of our innovation and a lot of our work goes into, is how can we make multiple petabyte data systems available in very short periods of time, sub-milliseconds, things like that. So I'll talk a little bit about those. Options under here are things such as search engines. So like our Facebook search has a very large amount of data, but it has to return results very, very quickly. So this is a very custom solution for that particular operation. Other things that fall into this are things such as stream processing. So in stream processing, we have a very large velocity of data, and then we can basically get it down to very small data sizes to make the response times very fast. So that leaves this other quadrant down here at the bottom. So this is small data, but really slow queries. That's not very interesting. So I'm not going to talk too much about that. We could ignore that quadrant for now. All right, so now what do we use? So the first one we have is MySQL. Hopefully most of you here know what MySQL is. Anyone not know what MySQL is? Good, you'll be at the wrong conference. So MySQL, we use this for a lot of different things at Facebook. So one of its primary uses is it's used for our primary graph data storage. So when you upload a status to Facebook, that status gets stored eventually in MySQL. If you upload a photo, the photo metadata all gets stored in MySQL. You become friends with someone, all that sort of information gets stored into MySQL. We also use MySQL for a lot of other systems as well. So we actually have a new system we're using which involves messaging. My colleague Domas will actually be talking about this system later this week. So if you want to see how we use MySQL for messaging, it's actually a new system that we've deployed that we're making use of now at scale. There's a lot of other applications as well. But MySQL is by far our most commonly used system for small data. So now when I say small data, what does that mean? So practically speaking, small data to us is tens of petabytes. So small is relative, right? So now across these tens of petabytes of data, we're looking at and generally get well under 5 millisecond response times. So very, very short, very quick type response times. How do we do this? And how do we store our data? Well, MySQL is used predominantly now in two different types of storage. So first is Flash. So we use a lot of Flash technology at Facebook. And then the second is through a system called FlashCache. So FlashCache is actually a system we built which is a hybrid flash disk system. So you can actually persist hot data on Flash and automatically migrate old data to disk. So it's actually a hybrid between those. So it still gives us very good response time of Flash, but then the efficiency cost of storing data on hard drive. And then across MySQL, we do hundreds of millions of QPS. So many, many queries at peak, reading lots and lots of small data bits. So the next solution I want to talk about is HBase. So we're a big user of HBase as well. So what is HBase used for? One of its big use cases is actually for Facebook messages. So messages that you send on Facebook via Messenger and so on will eventually end up in HBase for long-term storage. So we use HBase primarily on disk. So when we need a disk storage technology, HBase gets used very predominantly for that. So what is the difference between HBase and MySQL? So the big thing is the actual data structures used for storing data. So HBase uses something called an LSM tree. An LSM tree is a write-optimized data structure, which has better compression and other types of properties. But for something like messaging and archiving old messages, it's a very, very write-heavy operation. So lots and lots of messages coming in, and again, relatively rare reads of this older data. So if you're interested in learning more about LSM and HBase and other things, my colleague Yoshinori will be giving a talk later this week about kind of LSM usage at Facebook with HBase and then RocksDB, which I'll talk about as well. So how much data do we store in HBase? Again, tens of petabytes of data. Again, the data density is much higher because it's mostly on disk. We then look at doing millions of queries per second. So an order of magnitude smaller than MySQL. But again, that's because of the type of access and the desirability of the query latency and so on. And then practically speaking, under 50 millisecond response time. So a bit longer, but again, when you're dealing with disk versus flash, things like that, you have these types of considerations. So the next one I want to talk about is RocksDB. Who here has actually heard of RocksDB before? Pretty good amount of you, actually. That's good. So what is RocksDB? So RocksDB is an embedded storage engine that we've developed at Facebook. It's actually a branch of LevelDB. It, again, uses LSM trees. But it's basically when people want to build a new system that basically uses data in an embedded type fashion. So where you might be using normally an SQLite or something like that, we've developed RocksDB to be very, very efficient, very fast for both memory, flash, and also disk as well. So we have a lot of systems now using RocksDB internally. So whereas before, when someone wanted to build something like this, it would often go to custom data stores. So we'd have someone say, hey, I want to create something for Newsfeed. They'd whip up their own data persistence layer, and they'd be good to go. However, you don't want to have too many data persistence layers, right? So RocksDB has become the go-to choice. It is now used by hundreds and hundreds of internal services at Facebook. One of the big users is actually Facebook Newsfeed. So when you go to your Newsfeed and you see your data coming up there, the history of everything going on and so on, that data is actually now being pulled from RocksDB. For our Newsfeed deployment, RocksDB does around 9 billion QPS at peak. So it's super heavily used, very, very fast storage technology at Facebook. It is open source, by the way, so you can go use it, create your own newsfeed that does 9 billion QPS if you really want to. All right, so now we're getting over to big data. So big data, we have some of the traditional big data options, for example, Hive. So Hive was originally developed at Facebook. We use HDFS. We use all the normal Hive tooling you would expect around it. This is the big warehouse that we have, distributed data, multiple regions, all this complexities as well around this. So practically speaking, Hive looks at queries from a minutes, hours type solution. So when you want to run a big pipeline that runs once a day, you want to run some query that scans terabytes of data, this is the option for you. Our data warehouse is currently well over 300 petabytes logical size. This is kind of old. It's actually quite a bit bigger than that now. But we have hundreds and hundreds of petabytes of data stored within our HDFS and Hive systems. And then practically speaking, the actual query processing, the selects and so on that are going on, is we actually process and read over 10 petabytes of data every single day in order to return our results and do our calculations and so on. So it's a very busy system doing lots of CPU, a lot of disk activity and so on in order to process over 10 petabytes of data every single day. So Hive works really good for a lot of things. However, one case where it doesn't work really well is when you actually want to sit down and run a query. So the problem is you sit down, you run a query, and it takes 15 minutes. That's a long time to wait for data. We have a lot of data analysts, business analysts, and so on that actually want to be able to do more interactive type operations as part of their everyday daytime job. So we actually developed a new system called Presto. Who here has heard of Presto? A little bit fewer of you. So Presto is an open source distributed query engine. The big difference between something like a Presto and a Hive is Presto works all in memory on a streaming basis, whereas Hive uses MapReduce with actual disk checkpointing and so on. What this means practically is it means queries are much, much, much faster in Presto. So like you may take a 15-minute query, and now it takes 10 seconds in Presto. The big difference, though, however, between them as well, the trade-off there, is Presto doesn't really handle failures well. So if it's running across 100 nodes, one of those fails. In Presto, your query says, oops, sorry, try again. Whereas in Hive, because of checkpointing and so on, it's able to retry and continue on. So where Presto works really, really well, and what it's used for is for when you're dealing with seconds or minutes types queries. So even if something fails, you can just basically run it again, and it'll work the second time. So we have a lot of adoption of this internally. Again, it is an open source project. There's actually being adoption by external users as well. Netflix and some other people are actually now starting to use Presto quite a bit. For our internal users, we do over 10,000 queries per day. May not sound a lot when I'm talking about 100 million QPS, but keep in mind these are very big analytic type queries. Doing aggregations and joins across 50 tables and all those sorts of things. For these 10K queries, we actually process over 30 trillion rows per day. So very big, expensive queries, but they return much faster in something like Presto. So the last option I want to talk about is another system called Scuba. So Scuba fits into our various category up here. So we actually wrote a white paper about Scuba. Unfortunately, it's not open source, but there is a white paper where you can read all about how Scuba works. But what Scuba is Scuba is basically a real-time analysis tool that we use for debugging and understanding what's going on at Facebook. So when you have a system as big as Facebook, our mobile applications, and so on, there's a lot of data that's generated. So we can look at things such as web requests and errors and so on and so forth. And if we want to break down real-time information, this is where Scuba comes into play. So for example, if I want to go and say, OK, who's gotten an error on Facebook, and we can break it down based on countries. So I could say, give me all the errors generated by users of Malaysia, from Malaysia on Internet Explorer 6, something like that. And we can do that basically in real time. This data comes in, and I can even do that and say, what happened in the last minute? So lots of data being generated, lots of data velocity for Scuba. So what Scuba actually is it's basically a leaf aggregator in memory columnar store. So basically, it takes in this huge flow of data, stores it in memory, gets great compression because of the columnar format, and is then able to answer very big, expensive queries kind of in a real-time fashion. So we're able to debug and dive down on what's actually going on Facebook in completely real time. So practically speaking, it's in the hundreds of terabytes of data size. Again, it is an in-memory data store, so it obviously can't consume too much. But it has a lot of things built in order to make it fit essentially in memory. It has concepts such as sampling and other sorts of statistical things it can do in order to essentially fit all the data in memory. And it has many millions of rows ingested. So again, the data velocity, very, very high, but it's able to keep, and because of these various systems, able to keep it in memory, and so on. So the final thing I want to talk about is two new systems. So these are systems that we've created kind of recently, we're looking at creating, that essentially fit into new places on that chart. So the first one I want to talk about, that I'm excited to talk about, is RocksDB and MySQL. So we're basically taking MySQL, which is well supported. We use replication. We have all the automation, everything around it. And we're basically going to plug in the RocksDB storage engine. So we're going to create a new storage engine around RocksDB. We're kind of calling it MyRocks, but you can name it whatever you want, essentially. And then we're going to use this for storing data as well. What's the advantage? Well, you have InnoDB, which is more of a read-optimized store, and then you have RocksDB, which is a write-optimized store. So that basically allows us to fit MySQL into a different location based on data write patterns and so on. So I'm kind of putting it right there on the chart. We'll see where it actually ends up in practice. But again, very fast writes. Data compression is better than InnoDB, depending on the different needs we need there as well. Again, Yoshinori will be talking a bit more about this at his talk later this week. So the other one I want to talk about is Presto plus MySQL. So I talked about Presto. Presto is our distributed query engine, right? So you can write SQL. It'll distribute it across 100 nodes, run those all in parallel. Well, what we've done is we've now made a sharded MySQL setup that Presto then runs on top of. So you can actually run a single SQL statement that will end up reading data from 100 database servers in parallel. And it can actually do parallelization even within that database server as well. So what we're able to do is we're able to do these analytic queries that can pull data and actually pull hundreds of millions of rows per second from MySQL. So whereas normally when you're doing analytics in MySQL, you'd be bottlenecked to a single server, this can be distributed across everything. The advantage of this is that MySQL gives us all the abilities of MySQL, right? We have all the replication, we have all the failover, we have all that set up, but it also gives us things like updatable data. So most analytic systems, once you write data, you can't update it anymore. With MySQL, we can actually update things, so we have constant flow of data. We can update historical data, we can access old data, and so on, without any problems at all. We're actually now using this in production for some of our analytic systems. So some of our external user-facing data can actually be seen through this setup. So this fits kind of into this category, where again, it has bigger data. So again, lots of nodes of data, but you can access them across single systems to get these more real-time analytic workloads. So that's basically it. So essentially, I wanted to give you some insight into how Facebook thinks about data, how some of our different data solutions look, how we use them, and how the polyglot persistence idea is important for the continuing world. So thank you very much. I can now pass it back to Jim.